Radio astronomy. I'm sure some of you have heard of it, but others probably don't even know what radio astronomy is, or what the differences are between radio astronomy and optical astronomy. Well, today I'm here to show you the differences between looking at the stars through an optical telescope and looking at the stars through a radio telescope. Let's take a quick history of radio astronomy so we can better understand what we're actually thinking about when we're thinking of radio astronomy. Radio astronomy was born in the early 1930s by a guy named Carl Jansky. Jansky was working at Bell Labs, a telephone company, and they were trying to determine what the source of noise on their 20 megahertz receivers were. To do this, he built a big steerable antenna to try to pinpoint where the noise was coming from. After a while of searching, he determined that his noise that he was picking up came from extraterrestrial sources. However, not too many people were interested in his discovery. But there was one guy. This guy was named Grote Reber. He determined that the signals were from a thermal origin and would be more easily detected at higher frequencies. While Jansky was working at the 20 megahertz range, or the 15-meter wavelength, Reber wanted to look at the 3000 megahertz, or 10 centimeter wavelength. To do this, he went on and built the first parabolic receiver, or reflector radio telescope. It's the kind of telescope that we know and see everywhere when we think of radio astronomy. It wasn't for quite a while later that we determined that most of the radio waves that Jansky and Reber were picking up were coming from neutral hydrogen, or 1420 megahertz, which is the 10 centimeter wavelength. Now, there are a few advantages to radio astronomy over optical astronomy. One notable advantage is you don't have to be out at night to do it. Another one is cloud cover really doesn't affect it too much unless you're in some weird, real high frequencies. But at neutral hydrogen, cloud cover isn't even an issue. Now, there are some disadvantages too to radio astronomy. While there's light pollution for optical astronomy, there is radio pollution for radio astronomy. Radio astronomy needs to be done in a very radio quiet zone. That's why the NRAO was created, or the National Radio Astronomy Observatory. It is a place in West Virginia, Green Bank, West Virginia to be exact, that is the National Radio Quiet Zone, meaning there's no cell phone towers, there's no wireless internet, nothing, no radio, nothing like that. It is 100% dedicated to radio astronomy, and that is all that happens there. NRAO was founded in 1956 in Green Bank, West Virginia. The first telescope at the observatory was an 85-foot parabolic reflector telescope. It was completed in 1959. The next telescope was at the time one of the larger telescopes in the world, the 300-foot telescope. It was completed in 1962. Then followed by the 140-foot telescope, the world's largest equatorial-mounted telescope, completed in 1965. And the current telescope that is in use right now is the Green Bank Telescope, or the GBT. It was completed in 2001. The Green Bank Telescope is the world's largest fully steerable object on land. There are also many other radio telescopes at the NRAO. One constantly is observing the sun, one is a remote-controlled telescope that was originally built by the Navy, and one is a tiny little 40-foot telescope that is used for educational purposes. I at one point had the chance to use this telescope a few times in order to observe at 1420 megahertz, or 20 centimeter wavelength. Now here's what a typical scan or observation on the 40-foot would look like. On either side there you have calibration marks, so you can tell exactly how hot something is in radio. And in the center, where it peaks up, is right when we're passing through the object. Just like optical telescopes, radio telescopes have resolution. Let's take a look at the Green Bank Telescope for a minute. The Green Bank Telescope has a resolution of 1 arc second, which is like looking at a pizza and being able to pick out the individual pepperonis from about 10 miles away. Looking back at the 40-foot telescope, it has a resolution of about 5 degrees. Now, as you can imagine, the Green Bank Telescope is much more accurate than the 40-foot telescope. They can pinpoint some of the smallest objects in the universe with the Green Bank telescope. Radio sources are measured in Janskis. It's a measure of how bright a radio source is to a radio telescope. The moon is very, very hot, or it has a lot of Janskis. Smaller sources like pulsars, quasars, all other small objects in the universe have a very low Jansky rating of in the 0.000 Janskis range. The 40-foot telescope, for example, can pick up about 10-15 Janskis. The Green Bank telescope can pick up anything from extremely bright sources down to the smallest number of Janskis that we know exists. The main idea here is, though, that the optical light that sources give off is in no way related to the radio light that they give off. Radio signals can come from almost anything in the universe, just like the cosmic radio background, or galaxies and quasars and pulsars hidden behind giant clouds of dust. There have been several different maps of the galaxy in different frequencies, and just like with optical astronomy, we can look at the spectral lines of galaxies and dust clouds and all sorts of extraterrestrial objects and determine exactly what they're made up of. Just by a simple Doppler shift, we can tell which way it's moving or how fast it's moving even. Radio astronomy and optical astronomy both have their uses in the world. Radio astronomy can find many objects that optical astronomy can't find. However, optical astronomy can find objects that radio astronomy can't find. It's both necessary to be able to know the vast place that is this universe.